to another video. In this video, we're gonna be talking about benzene. We're gonna be using a few terms such as nucleophile and electrophile, nucleophilic substitution, electrophilic addition, and such. So, I'm gonna suggest that you go and check out one of my Instagram posts. I'm gonna put a link in the description that explains all those things. You can go and check it out before watching this video. So, anyways, let's get right into it. So today we're gonna talk about benzene, one of the most crucial molecules in organic chemistry. Now, these what you're seeing here are the skeletal structures for benzene. So everywhere there's a point on the hexagon, it's assumed to be a carbon, and all the bonds that are not carbon to carbon are considered filled by hydrogen. So it is assumed there's a hydrogen here, hydrogen here, a hydrogen here, a hydrogen here, a hydrogen here, and a hydrogen here. Same thing for these other two. So what you're seeing here and here are the two first proposed structures of benzene. However, if we use benzene like either one of these, it will act like an alkene and undergo addition reactions, but it doesn't. It instead only undergoes substitution reactions. So what happens is that benzene undergoes conjugation and forms a resonance structure looking like this right here. So this is the true representation of benzene. So what we have here is a ring of electrons forming a pi bond surrounding the entire molecule. And what that creates a region of high electron density that is attractive to electrophiles. Now, as I said before, benzene only undergoes substitution reactions, and so it is these reactions would normally be referred to as electrophilic substitution. Now, benzene can undergo addition, but it takes very, very high temperatures for it to undergo addition. So, first thing we'll be looking at is the halogenation of benzene. Now, as I said before, benzene is quite stable, and so in order for benzene to be halogenated, it must be reacted with what is known as a Fidel-Crafts catalyst. So let's say we want benzene to become bromobenzene, we will react it with bromine liquid, but we'll use FeBr3 as the Fidel-Crafts catalyst, and the result is going to look like this, where we now have one of the hydrogens on, on the molecule being replaced by a bromine, and then we will have HBr as another product. So of course the hydrogen coming off of this reacts with the other bromine atom to form that, and of course the Fidel, because it's a catalyst, it comes out as it was before. AlCl3 aluminum trichloride can also be used in order to facilitate this reaction. The other reaction we'll be looking at for benzene is the nitration of benzene. Now, the nitration of benzene takes place by using the nitronium or nitrile cation, or NO subscript 2 plus nitrile ion, but it cannot be activated on its own, so it must be generated in a reaction mixture by mixing sulfuric acid with nitric acid at a temperature of about 50 to 60 degrees Celsius. So if we react H2SO4 with H NO3, and the catalyst will have a temperature at about 50 60 degrees. This is in Celsius, of course. We'll end up with the bisulfate ion so the bisulfate ion plus the hydronium ion plus the nitrile ion, which is the one you want for this reaction. If we balance this, we would put a 2 here, a 2 in front of the sulfuric acid, and yeah, that's about balanced. That's about balanced. So now, now we would have generated this. The nitrile ion would be attracted to the highly negative electron density in the benzene system and will go on to form nitrobenzene with NO2 replacing one of the hydrogen ions. And of course, the hydrogen ion that comes off will end up reacting with the bisulfate ion, recreating the sulfuric acid. Hence, the sulfuric acid can be thought of as a catalyst in this as well. Now look at another form of benzene known as methyl benzene, and that is where we have one of the hydrogens in the benzene being replaced by a methyl or a CH3 group. Now in this, the methyl group on the benzene ring tends to be electron donating and has a positive inductive effect, pushing the electron density towards the ring, thus making the system more susceptible to substitution. So if we were to do halogenation on this, we would not require the Fidel-Crafts catalyst. We would just have our bromine liquid react with this, and we would end up with now a general rule when you are dealing with other forms of benzene, like methyl benzene or nitrobenzene, whenever you are say halogenating it, the halogen will go on either the second, fourth, or sixth position, known as the second and the fourth. The fourth is known as the para position, while the second and the sixth is known as the ortho position. The fourth is known as the para position, while the second and the sixth are known as the ortho positions. Now, just like how we could nitrate benzene, we can also nitrate methyl benzene, which again is much easier than with normal benzene due to the higher level of reactivity. the nitrile ion would be once again created in the same mixture as we had up here before, and we would react the methyl benzene with that mixture, and we would end up with the two forms as we had with the halogen. So we end up with the methyl group keeps its position, and then the nitrile group would be formed here, and would once again be formed down at the para position down here. Now when you react it, what you'll notice is that there's going to be a 1-to-1 ratio of both of these products. So this is gonna be a 1-to-1 ratio of this and a 1-to-1 ratio of this. Now, last and most important thing you must know about benzene is that compounds with benzene rings are known as aromatic compounds. Compounds with benzene ring are known as aromatic compounds, as opposed to non-benzene compounds that are known as aliphatic. That will be all for this video. Thank you for watching.
Tell me pretty lies, look me in the face, tell me that you love me.